star 1,470 light-years away just blinked. Its brightness dropped by 22% in data captured by the Kepler Space Telescope, and no planet in existence could ever do that. Scientists have 22% worth of proof that something dark is sitting between us and that star, but nobody can agree on what it actually is. An object roughly 1 billion square kilometers across, nearly 2,000 times the surface area of Earth, a scale of engineering no known civilization should be capable of. So what exactly is standing between us and a star? An alien megastructure, or nothing more than cold, drifting dust? When NASA's Kepler mission first turned its eye toward a patch of sky between the constellations Cygnus and Lyra, its job was simple. Watch for the tiny rhythmic dimming that happens when a planet crosses in front of its star. Over the course of the mission, Kepler confirmed 2,662 planets this way, each one announcing itself with a small, clean, predictable dip in starlight. KC 8462852 never made that list. It sat in Kepler's field of view, producing dimming events so strong they should have been the easiest catch of the entire survey. And yet nothing about them behaved the way a planet should. The star eventually picked up a nickname that had nothing to do with its catalog number. It became one of the very few stars in modern astronomy named after a living scientist, Tabby's star, after Tabitha Boyajian, the astronomer who first flagged its strange behavior with help from citizen scientists on the Planet Hunters platform, a project built specifically so that ordinary volunteers could scan Kepler's raw light curves for anomalies the automated software might miss. When Boyajian and her team first looked closely at the data, their instinct was that something had gone wrong with the instrument. Surely a sensor glitch, a processing error, anything but a real signal. But the dips kept showing up, deeper and stranger than anything in the rest of the Kepler catalog, and after ruling out one explanation after another, she finally admitted, "This is a weird star." One of her early hand-annotated charts, still preserved in the Yale archives today, carries a scribbled note in the margin that says simply WTF. Shorthand, she later explained, for "where's the flux?" It is a small human detail that has outlived the paper it was written on. Part of what makes the star's behavior so puzzling starts with its basic physical profile. KC 8462852 has a surface temperature of about 6,750 Kelvin, noticeably hotter than our Sun's 1,078 Kelvin, placing it in a class of younger, more massive stars, exactly the kind of star still expected to carry disks of leftover dust and debris from its formation. That alone isn't unusual. What's unusual is what came next. Once the strangeness of the light curve was undeniable, the question stopped being, is this a mistake, and became, what could possibly cause this? And one answer, when it arrived, was more provocative than anyone expected. In 2015, astronomer Jason Wright of Penn State University put forward an idea that turned a quiet Kepler anomaly into an international headline. What if the dimming wasn't natural at all, but the signature of a massive structure built by an advanced civilization designed to harvest energy directly from the star? For a dip of 22% to occur, whatever was blocking the light would need a surface area roughly 1,000 times the size of Earth. Large enough that megastructure wasn't just a dramatic word, it was closer to a literal description. The idea spread almost instantly. Within 2 weeks of the first news coverage, the story had been picked up by more than 20,000 websites and blogs, most of them leading with a single word: aliens. For a brief moment, an obscure star catalogued only by a string of numbers became one of the most talked about objects in the sky. But the Dyson swarm idea comes with a built-in problem, and it's a problem written directly into the physics of how such a structure would have to be built. If an advanced civilization were steadily constructing solar collectors around their star, decade after decade, the dimming should increase gradually and predictably as more panels went up. That isn't what the data shows. Instead, the dimming events appear and vanish quickly, with no sign of a slow engineered build-up over time. Is there any chance the star is broadcasting something we could actually detect? Researchers pointed the Green Bank radio telescope at Key 8462852 and searched the 1.1 to 1.9 GHz band for narrowband signals, the kind of tight artificial signal a transmitting civilization might produce. They found nothing. No radio chatter, no deliberate beacon, no sign of active communication of any kind. And yet the hypothesis has never been fully closed off. In surveys of the scientific community, 36% of respondents said the possibility of an artificial origin couldn't be ruled out entirely given current evidence. A reminder that most astronomers favor a natural explanation, but a genuine minority still keeps the door open. Once the alien explanation had been pushed to the margins rather than eliminated outright, the search turned toward the sky's more familiar troublemakers. One detail made the alien hypothesis hard to sustain from the start. The dimming events of Tabby's star have no stable rhythm at all. A single dip can last anywhere from 5 to 80 days, a range far too wide and irregular to be explained by one object on one predictable orbit. So what could produce something this messy? Boyajian herself proposed one of the earliest natural explanations, a swarm of comets, a loose cluster of icy bodies sweeping past the star in staggered, overlapping paths. The scale required is staggering on its own. Calculations suggested it would take roughly 648,000 giant comets all clustered together to produce a 22% dimming event. Later analysis complicated even that picture. When researchers examined how the star's brightness dimmed and then recovered over its first 2 years of observed dips, they found none of the spectral fingerprints you'd expect from ice or carbon dioxide, the very ingredients a comet swarm should be made of. What the data pointed to instead was something closer to fine metallic dust, more consistent with the debris of a shattered asteroid than a cloud of icy comets. The push to get better data didn't come only from professional observatories. In 2018, Boyajian and roughly 200 collaborating scientists ran a crowdfunding campaign to buy dedicated observation time on the Las Cumbres Observatory network, hoping to catch a dimming event in real time with instruments capable of reading its color and composition. The campaign raised over $100,000 from at least 700 individual backers in a matter of days, blowing past its original $36,000 goal. It worked. Astronomers caught a live dimming event but found no trace of the radar or laser a technological civilization might leave behind. That success fed directly into an even larger coordinated effort. May 2017, as the star began dimming again, astronomers mobilized roughly 30 telescopes around the world, including Kepler itself, now running in its extended K2 mode, all pointed at the same patch of sky at the same time. The observation campaign that followed finally gave scientists the kind of decisive spectral data they needed. By 2018, new analysis of that hard-won data pointed toward an answer that was almost anticlimactic after years of speculation. The dimming looked like the work of ordinary inorganic dust, specifically silicate particles, absorbing starlight rather than any solid object passing in front of the star. Here's the clue that clinched it. During the 2017 dimming event, blue wavelengths of light were blocked more strongly than red wavelengths. That kind of wavelength-dependent dimming is a textbook signature of fine micron-scale dust, and it rules out a solid object almost completely, since a solid body would block all colors of light more or less equally. Computer simulations run in 2019 modeled how such dust clouds would behave, and the results matched the star's observed pattern strikingly well. Deep dimming with an erratic, predictable recovery, consistent with more than 750 days of actual observational data. Those simulations pointed to something specific. The dust clumps had unusually low density, the kind you'd expect from the scattered remains of a shattered smaller body rather than a compact, solid structure. But could this dust simply be hot debris glowing from its own heat? If the material absorbing the starlight were sitting close to the star and heating up, it would need a temperature above roughly 1,500 Kelvin to radiate detectable heat of its own. Infrared observations found nothing close to that, no heat source above about 500 Kelvin anywhere near the star. Whatever is causing the dimming is cold, and it sits far out from the star itself. That conclusion is reinforced by how quickly the star bounces back. The largest dimming events on record, in 2011 and 2013, recovered within about 30 days. Whatever material caused those dips must have been enormous, and yet fragile enough to disperse or drift out of view almost as quickly as it appeared. The spectral data had answered one question and opened another. If this dust is cold and distant, what does that tell us about where it actually comes from? A 2-year monitoring campaign using NASA's WISE infrared telescope running from 2018 to 2020 found no excess heat radiating from the space around the star at all. That single result quietly ruled out one more possibility. A massive cloud of matter that was actively collapsing and heating up as it condensed wasn't sitting there. Whatever was blocking the light wasn't warming anything up. NASA's Spitzer space telescope was brought in to settle the question further, specifically checking for infrared absorption around KIC 8462852, the kind of signature any substantial cloud of surrounding material should produce, warm or cold. Spitzer found essentially nothing in the infrared range. That absence is itself the evidence. It confirms the material has to be extremely cold and made of exceptionally fine dust, too faint and too diffuse to register as a heat source at all. Data from the European Space Agency added another layer of consistency. Tabby's star showed no major variation in its light curve at longer infrared wavelengths, even during periods when it was dimming sharply in visible light, meaning there's no dust anywhere nearby that's heating up in response to the star's radiation, despite how dramatic the dimming looks to the naked eye. Underneath all of these short, sharp dimming events, Kepler's long-term data revealed something slower and stranger. The star's overall brightness declined by about 3% over 4 years, from 2009 to 2013, a gradual fade that set it apart from every comparable star in the same patch of sky. So the picture that emerges is one of something cold, faint, and mostly invisible, except when it happens to cross directly in front of the star. To understand where material like that comes from, it helps to look at a star going through something similar in real time. Could a completely different famous star show us the same mechanism in action? In 2019, Betelgeuse, the bright red supergiant in the constellation Orion, went through its own unexpected dimming episode, and this time astronomers had a front row seat. The cause turned out to be dust, expelled from the star during a genuine mass loss event. No artificial explanation required, no ambiguity left hanging. It gave astronomers a real observed example of exactly the mechanism many suspected was happening around Tabby's star. A similar pattern shows up elsewhere too. The star Epic 24789 exhibits its own unusual dimming, but far more extreme, dips as deep as 65%, and the star itself is much younger. That combination suggests a disk of collisional debris, chunks of material grinding against each other and generating dust, could naturally explain events like this across a whole class of young stars, not just one anomaly. Closer observations of KC 8462852 in 2020 added one more piece to the puzzle. The dust around the star isn't spread out evenly. The deepest dimming happens when a thinner section along the star's equatorial plane passes in front of it, rather than material near the poles. A detail consistent with dust concentrated in a disk-like structure rather than a random, chaotic cloud, and further evidence that this is a natural, structural feature of the system rather than anything engineered. With a natural mechanism now backed by a second, independently observed star, the story of the star starts to look less like an unsolved anomaly and more like a lesson in how long it actually takes science to catch up to a strange result. Alexander Fleming discovered penicillin in 1928, almost by accident, when he noticed mold-killing bacteria in a forgotten petri dish. It took until 1941, 13 years, before it was used to treat a human patient. Confirming what Tabby's star actually is has followed a similarly slow, deliberate path, built one observation campaign at a time, rather than one dramatic announcement. The research hasn't slowed down. As of 2023, more than 883 scientific papers referencing KC 8462882 had been published and indexed on Arxiv, making it one of the most written about individual stars of the past decade. A remarkable output for an object that isn't even a confirmed exoplanet host. The sustained attention shows up in more than just paper counts. 3 major studies on the star have appeared in the Astrophysical Journal, one of the field's most respected publications, and nearly every major astronomy conference held between 2016 and 2023 has featured a dedicated session on it. Few individual stars get that kind of consistent institutional attention. That level of interest even reached funding decisions at the highest level. In 2016, NASA awarded Boyajian roughly $120,000 to continue her research into the star directly, a clear signal that a major space agency considered the mystery worth serious, sustained investment, not just a passing headline. If a discovery this strange took years of patient, methodical work to explain, that raises a practical question for the rest of us. How do you tell the difference between a real mystery and a manufactured one while the story is still unfolding? In an age where alien signal detected headlines show up in your feed on a fairly regular basis, it helps to have a quick, repeatable way to separate a genuine mystery from clickbait dressed up as one. Here's a simple process for checking any unusual astronomical claim before you share it. First, confirm the star's actual designation, its CAS Gaia or other catalog number, and look it up directly on NASA's own databases rather than trusting a headline's description of it. Second, find the original scientific paper on archive.org itself, not a second-hand summary written for a general news outlet. Third, check whether the observation has been independently confirmed by more than one research group. A single team's result is a starting point, not a conclusion. Fourth, check specifically whether the alien explanation has actually been ruled out by the paper, or whether that's just how the headline chose to frame it. Fifth, compare the star to other confirmed variable stars with similar behavior, since genuinely unique signals are far rarer than headlines suggest. Beyond the story itself, it's worth knowing how to search for the underlying evidence. Start with the primary source. Information coming directly from NASA or SETI carries more weight than a blog summary of it. Use Google Scholar with a precise search like K8462852 or Boyajian star to see what's been published in the last 5 years. If you check Wikipedia, don't stop at the article text. Open the citations at the bottom and click through to the original sources they're built on. For anything involving light curves or brightness data, cross-reference public databases like exoplanet.eu or MAST, which host the raw observational data astronomers actually work from. And always ask a simple question before believing a dramatic claim. How many independent research groups have actually confirmed this? Tabby star is a near-perfect case study in why this matters. Headlines called it the alien megastructure star for years, and that framing is still what most casual searchers turn up first, even though the actual scientific evidence points consistently and repeatedly toward cold natural dust. The gap between the headline and the paper is exactly the gap this 5-step process is built to close. Knowing how to check a claim is one thing. Understanding why so many people wanted this particular claim to be true is another story entirely. Why did one obscure Kepler target capture more public imagination than most confirmed exoplanets ever have? In 2015, alien megastructure star became one of the most searched astronomy phrases online, with articles about it drawing more than 2.5 billion combined page views across science news sites, outpacing coverage of nearly every other astronomical topic that year. That fascination didn't stay confined to news articles. Major science YouTube channels picked up the story, and Kurzgesagt's video framing it around the concept of the Great Filter, the idea that advanced civilizations might destroy themselves before they can be detected, went on to earn more than 25 million views. In the comments sections beneath it, plenty of viewers weren't just entertaining the megastructure idea. They were treating Tabby star as physical evidence that it had already happened to someone else. And yet, for all that speculation, the silence has been consistent. Even the Very Large Array, one of the most sensitive radio telescope systems ever built, has never picked up a single radio continuum signal from the direction of KI's T4628TIV2, despite some of the longest cumulative observation times dedicated to any single star. No detectable energy signature has ever turned up there, at any wavelength associated with active technology. The raw scale of the dimming itself is part of why the fascination has lasted. Across 754 days of combined observation, astronomers recorded dips as deep as 21.2%, home to at least 3 major episodes over 4 years. Never on a predictable cycle, always arriving as an irregular jolt in the data rather than a rhythm anyone could set a clock to. That same appetite for the strange and the unexplained hasn't stopped with Tabby star. It's part of why researchers keep watching for anything else that might behave the same way. Not every explanation on the table has been fully closed off. One remaining possibility is that the dimming comes from the remnants of a planet slowly evaporating as it orbits too close to its star, shedding a trailing cloud of debris that periodically blocks starlight, a hypothesis known simply as an evaporating planet. Could our own sun ever do something like this? In principle, yes. Any star can dim if a large enough object or debris field crosses in front of it. But the odds of a configuration this extreme occurring around a star like KC 8462852 are vanishingly small based on everything we currently know about planetary systems, which is exactly why this particular star remains, even now, essentially one of a kind. The scale involved is worth sitting with one more time. If the dimming really were caused by a single solid structure, it would need a surface area of roughly 1 billion square kilometers, nearly 2,000 times the surface area of Earth, just to block that much starlight. That's an engineering feat so far beyond anything modern science considers plausible for any civilization that the possibility, while never fully closed, keeps sliding further to the margins with each new piece of data. Behind all of this data sits the person who started the search. Tabetha Suzan Boyajian was born on May 5, 1980 in Istanbul, Turkey. She is an American astronomer of Turkish descent, now a professor at Louisiana State University, and her name is permanently attached to the star that made her career-defining discovery possible, a fitting symbol of what citizen science and sheer persistence can accomplish. Every hypothesis explored so far, from alien engineering to cold interstellar dust, eventually circles back to the same larger question about our place in a universe this vast and this strange. The journey through KIC 8462852 shows just how much room the universe still leaves for genuine wonder. A story that opened with the possibility of a colossal alien structure and closed, years later, with something far quieter. Cold silicate dust drifting through the dark. The story of penicillin taught us something that applies just as well here. Patience and rigorous verification are what turn a strange anomaly into real understanding, even when the process takes decades rather than headlines. Boyajian's Kickstarter campaign wasn't just a fundraising success story, it was proof that public curiosity can genuinely move science forward, that thousands of ordinary people caring enough to chip in can put a telescope where it needs to be at exactly the right moment. That kind of curiosity might be the most valuable resource in this entire story. So while researchers keep gathering new data and refining more sophisticated models, one question is still worth asking. Is it really an alien structure that would make us remarkable in this universe? Or is it simply our refusal to stop asking WTF that sets us apart?